Here's some quick help on the simulation for the riverboat. Think about the moving walkway. So you can see the first setup. The boat is actually going to be traveling in the same direction as the water's current. So it's kind of like walking in the same direction on the moving walkway. If you think about that, then we want the combined velocity. So relative to the shore, we have to factor in both the water's flow or velocity and also the boat's. This is just like walking in the same direction as the moving walkway. So if you find that total, which should be faster because you're going in the same direction, you can then use one of our kinematic equations to solve for how far down the river they've gone in a certain amount of time. One good thing about these problems is that there will not be any acceleration. So if you think about the equations, displacement equals vi times t plus 1/2 at squared, the second chunk of the equation will drop off and it'll simplify to just displacement equals the relative velocity multiplied by the time. One-dimensional should be pretty easy. Of course, you can reverse the direction by changing the boat's heading and make it go upstream, but I'm going to jump right to the big one where we're dealing with relative velocity or relative motion, in 2 dimensions. So right now you can see the current of the river is still south or downstream, we call it. And then the boat is actually heading across the river. So when you run the simulation, you'll see that, yes, they do get across the river, but they also get taken downstream. Well, think about what these velocities are. They're still vectors. So if you want to solve for the resultant, you would still do tip to tail, which would make our right triangle. And of course, you could do Pythag and some trig for any question that's asked. If, though, I ask you how long it takes to get across a river or how far downstream, you have to think specific to the component I'm asking about. So for instance, if I ask you how long it takes to get across the river, going across the river is the x component. So we only want to deal with values in the x component then, so figure out which relative velocity is in the x component. Use the displacement, of course, in the x component, and that could help you get the time. The nice thing is that time is a scalar and can be applied to both x and y components always. So if I then ask you how far downstream, again, think specific to the component I'm asking about. How far downstream is the y component? So I would want to use the relative velocity in the y component. I can use the time, because of course that's a scalar, and then I would be solving for the displacement in the y. So still think of vectors, but when I go to ask for things like time or displacement, you can't mix and match them. You can't combine x and y information, not even the velocity vectors. So you got to keep them separate and make sure you're using it just in the x or just in the y. All right. I will give you one final hint. The last part of this activity, I'm going to ask you basically how far upstream do you need to aim to end up directly across the river. So you would have to aim your boat some angle upstream, of course. I don't know, maybe it ends up being 35, just guessing right now. The interesting thing about this is when I actually aim it upstream, you would think that this velocity is the resultant because it's the hypotenuse. This is a very weird idea. It's going to kind of throw you off a little bit, but the hypotenuse is not technically always the resultant. So in this case, if you look, I'm actually aiming with the boat's relative velocity to the water. That's not a resultant. All right, the river speed, the water speed relative to the shore, will then bring it back down south a little bit, and the resultant is actually what the question asks. It's straight across the river. Okay, so take your time with that question. It's a little tricky.